Hello science people, Amy here. I am just making this video to talk through some quick concepts around the electromagnetic spectrum and how that relates to the light topic we're studying. So I'm just going to pause the recording quickly and then we'll go over to somewhere that I can take some notes for us. Okay, so I'm just going to minimize my window and fold my laptop around, and then we're going to start taking some notes. Just let me work out how to pause. And I'm just going to minimize my little window so you're not just staring blankly at my ceiling. So when we're talking about the electromagnetic spectrum, we're talking about a type of energy. So physicists believe that there are four fundamental forces in the universe. There's electromagnetism. There is the strong nuclear force that holds the quarks in an individual proton or neutron together. There's the weak nuclear force that holds protons and neutrons together in the nucleus. And then there's gravity. Electromagnetism is actually one of the ones we actually know the most about. So let's talk about the electromagnetic spectrum. Now, the electromagnetic spectrum, and this should be familiar to you from the little online simulator we did earlier in the week. The electromagnetic spectrum is all about waves. Now, when you do a bit more maths, you will learn that this is actually the shape of a sine or cos wave. Sine and cos, when you graph them in a particular way, forms this wave pattern. So let's define a couple of basic measurements that we can take of this wave. So the two main things that we think about are our wavelength, which is this length here. And then going the opposite way, let me just change colours, going the opposite way. So from the top of the peak to the bottom of the peak, we have amplitude. Okay, so this wavelength varies depending on the type of wave that we're looking at. So different waves have different wavelengths. So for example, we can measure waves in centimetres if it's a particularly long wave. It could be metres if it's a really long wave. The wavelengths of light that we see are measured in nanometers. Now, one of the things that is awesome about the metric system, each of these letters in front indicates a multiplier. So like a kilogram is 1,000 grams. A nano, so nano is the prefix, so a nanogram, just like a nanometer, it's 10 to the negative 9 meters. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So a nanometer is that many meters. So most of the colours that I'm looking at my screen and I'm seeing now, most of those waves of light have a wavelength that's that small. So sorry. The experiment that you're going to be doing at home next week, measuring how long a microwave is. Now, you think that a microwave might be even smaller? No, microwaves are actually reasonably large when it comes to waves. So another thing that we can talk about when we are talking about light waves is something called frequency. So let me find another colour. So frequency. That's how many waves per second? So frequency is measured in a unit. So just like wavelength is measured in, sorry, my notes have gotten a little bit messy. Just like wavelength is measured in units of distance, frequency is measured in a unit called hertz, which is Hz. So if something is 2 hertz, it's saying it's 2 waves per second. If something is 2000 hertz, it's 2000 waves per second. So when I am looking at frequency and wavelength, basically the smaller the frequency, smallest wavelength, so small wavelength is high frequency. So let's think about this in terms of energy, because energy is one of those super important topics that keeps coming up whenever we're talking about physics or chemistry. So if something is high frequency, there's thousands and thousands of waves that are hitting a point every second. So energy is linked to this frequency. So if something has super long waves, it's much lower energy than, oh, I've messed up my colours, sorry. If something has, and why I'm doing the waves like this will become obvious in a moment. If something has super long waves, they're going to have less energy than something that has a much shorter wavelength. So that purple, and I'm sorry if any of you are colourblind, that's going to be high energy. That red wave is going to be my low energy. So think of it like, so I can have a globe, like a normal light bulb on, and it doesn't burn me. So the waves of light being given out by that are lower energy than something like, and you guys have probably never seen one before, I hope you never have, the globes that are used in tanning beds, or the globes, sorry, not the globes, but the sources that give out X-rays. So basically, electromagnetic rays cover everything from radio through to infrared. So infrared includes things, so sorry, microwaves belong in here. Micro. Then we've got infrared. So infrared bulbs, you've probably seen them before. They are the light bulbs that are in restaurants. So if you're at a restaurant that's got like an open kitchen where the kitchen passes the meals to the servers and there's like a bar and there's like these reddish orange light globes over it that keep the food warm, they give out infrared radiation. Then we've got what's called the visible spectrum. Then as we continue on, we've got ultraviolet light. Now, UV light, we know that if, well, we're Australian, we know that if we're exposed to that for too long, it can cause DNA damage. So that's how So the UV light, the energy of that wave is enough to shake apart DNA and cause damage, which can lead to cancers. So as we go up from UV light, we've then got X-rays. So UV light can penetrate the top couple of layers of skin, give you a nasty sunburn if you fall asleep outside, and give you skin cancers if you're exposed to it for too long. But it can't penetrate further. So you can't get, say, throat cancer from a sunburn. That's not how, because the UV energy doesn't have, so the UV waves don't have enough energy to penetrate more than the top couple of layers of skin. X-rays, and I'm guessing all of you have had an X-ray at some point. X-ray waves have enough energy to go straight through all of the fleshy bits, but not enough energy to go through bone. So that's why on an X-ray, you can see the bones outlined. It's basically the shadow of where the X-rays can't go through and colour the film. So this is used for bone. Oh, be good if I could spell bone imaging. Further up from X-rays, you then have gamma rays, which is like Hulk. So that is the type. So as we go up, as we move from left to right across this list, I am increasing energy. As I move across, I am increasing frequency. And as I move across, I am decreasing wavelength. So my radio waves have a wavelength of, it can be up to a couple of 100 meters. So at the moment, me sitting here in my flat, I am being exposed to radio waves. Now, they're not harmful in any way. But if I was sitting here being exposed to X-rays all the time with that much shorter wavelength, so I told you visible were in the region of 10 to the minus 9 meters. X-rays and gamma rays are even shorter. So it's like 10 to the negative 12 meters. And I've got a graphic off to the side that I'm going to show you in a minute that has some proper numbers attached to this. So let's just look at these three descriptions here. Infrared, and again, I'll switch to red so it's appropriate. Infrared. So infra means below, and then red. And then, and again, I'll switch to purple because I'm obvious that way. We have ultra violet. So ultra means above. So 5-second hypothetical. Hopefully you see where I'm going. Inside this visible spectrum is the entire rainbow that we're used to seeing. So you've heard, like, you know the acronym ROY-G BIV, red, orange, yellow, green, blue, indigo, violet. Looking at what's on either side of that visible spectrum, we have infrared, then the visible spectrum, then ultraviolet. It should be pretty obvious that that is the order of colours. So we start with red, we move through and we get green. Then we go through to, I don't have a purple. Oh, more colours. Where's my purple? There's my purple. Yes, that's my purple. Through to violet. So that's my rainbow. And for reasons that we will talk about later, when the rainbow forms, there is always one colour that bends more than the others. The rainbows always form with the same colour down the bottom of the curve rather than at the top of the curve. So that is a quick little nutshell introduction to how we measure waves, the link between wavelength, frequency and energy, and how that relates to some of the forms of electromagnetic radiation that you've probably already heard of. So here is a nice diagram that I found. So AM radio. So have you ever been like out on a drive in the country and all of the radio stations have stopped except for like ABC AM? That's because those waves are super long and they're able to be transmitted a very long way without them losing the energy that encodes the radio signal. So that has a wavelength of about 500 meters, and it has a frequency of about 10 to the 6. As we move in, we get normal radio and TV waves. So we have the FM stations here, which is what normal car radios pick up, as well as AM. And then we've got UHF, which is what walkie-talkies work off. So walkie-talkies don't work over a super long distance. That's because as those wavelengths get shorter, they lose their energy faster. So microwaves, the experiment that we're about to do, those, depending on the exact energy that your microwave has, can have wavelengths between about 1 and 6 centimetres. Thermal IR is, if you've ever seen, like maybe in a movie or a computer game, like the heat vision goggles, that's what thermal IR measures. So that's body heat. And it has a wavelength of about 100 micrometers. So 100, so micro is a Greek letter, and in measurements, it means 10 to the negative 6 meters. And it has a frequency of somewhere between 10 to the 13 and 10 to the 12. You've then got infrared, and then the visible spectrum. Look at how tiny that is. Everything that we visually experience of the world exists in a tiny range of wavelengths. So the purpliest purple that anybody has ever seen has a wavelength of about 400 nanometers. So that is 400 times 10 to the negative 9 meters. So let's actually show that as a decimal to show us how small that is. So 400 decimal point. So I'm going to move that 9 spaces to the left, and I'm just going to change colours so you can see me doing it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where my decimal point ends up. Now let's put in 1, 2, 3, 4, 5, 6. So 400 nanometers, the purpliest purple that anybody has ever seen, is 0.000004 meters. Now, let's have a look at what the reddest red anybody has ever seen is. That's 700 times 10 to the negative 9 meters, which is 700 decimal point. So let's again count out. 1, 2, 3, 4, 5, 6, 7, 8, 9. My decimal point ends up there. 3, 4, 5, 6. Okay, so the reddest red that anybody has ever seen has a wavelength. The length of that wave is 0.000007 meters long. You've then got ultraviolet rays, which are the ones that burn our skin. X-rays, which are the ones that go through our fleshy bits, but not our bony bits. And then gamma rays go through everything. So an angstrom, which is this A with the circle on top, that is a unit of measurement that is used only for stuff that is like at the atomic size. So when we start talking about gamma rays, we are talking about like nuclear physics. Gamma rays are produced from nuclear explosions, from radioactive decay. And its frequency is super, super high. So these gamma rays are our super high energy. Whereas I am exposed to radio waves every single second of every single day, and they don't hurt. They don't cause any damage to us because those waves are such low energy. Okay, if I get some questions on it, I'm happy to explain why we can see these colours. That's something that we might actually talk about towards the end of this light and sound topic. But I did just want to introduce you to what are the basics of how we can measure and talk about waves and the link between energy, frequency, and wavelength. Okay. Oh, sorry, I didn't mean to hit that. Thank you so much for watching this video. Hopefully it's clarified some of your questions about how light works and how the electromagnetic spectrum works. For some of you, it might have been a surprise that all of these different forms of energy are really only one form of energy, just with different wavelengths. Thank you so much for your attention, and I will see you next time. Bye.